Good afternoon, everyone. Welcome to the Horyzn concept presentation. I'm Balázs, and we are here today to speak about our concept, what we called Horyzn. Two notes at the beginning. First, we have set a time for the questions. At the end of the presentation. Second, because of privacy rights, the Q&A session will not be transmitted via YouTube. You can also find our agenda in the lower part of the presentation. Our story began about 8 months ago when we decided to participate in the NFC international competition. The task is to build a fixed-wing aircraft that is able to take off and land vertically. But our aircraft has to be energy efficient, and we get the most of our points for the flight performance. So the total distance divided by the energy consumption. We must also have an innovative design. We have to fly fully electric, and we must carry a 2-kilogram payload measuring about 1 meter. The competition will be taking place in the end of October. The mission profile is quite challenging and includes a taxiing 15 minutes cruise flight with a minimum flight speed of 16 kilometers per hour and also looping. So we put this team together. But who are we today? We are 29 bachelor, master, and PhD students. We are from 9 different nations. We are divided in 7 sub-teams. And we have one goal, to win the NFC competition. So we have started the brainstorming process to find an optimal configuration for our mission. We have studied the following configurations: the tail-seater, the tilt rotor, the kestrel, the tilt wing, the quad plane, and the quad plus tilt configuration. From the quad plane and the quad plus tilt configuration, we derived the final concept. I'm proud to say that we finally find a configuration that we called Horyzn. Horyzn is derived from its design goal to be ultra efficient. Deploys 4 hover rotors mounted on booms at the wing and 2 wingtip cruise engines. This innovative configuration combines the simplicity of a conventional quad plane configuration with a high maneuverability during the hover phase and a high overall efficiency. The separation of the hover and cruise propulsion simplifies the system complexity and making it less complicated to design and safer to operate. But what advantages do we have with the wingtip rotors? The operating in completely undistributed free stream conditions improves performance significantly. By interacting the wingtip vortex, the proposed design partly cancels out the induced drag and the wingtip. Deploying differential thrust technology, a high U authority during the hover phase is made possible. This enables a precise hovering and a high level of control that other configurations cannot provide. And since the differential thrust technology is also used during the cruise flight, no rudder is required. So after we selected the configuration, we started the design process. But what does our design process look like, and why is it so special? To explain that, please welcome from the design loop team, Heitor Gardner.
Thanks, Balázs. Hello, everyone. So let's start with the design loop process. Quick introduction in the beginning into this topic. So the problem when we want to design an aircraft is that everything influences everything. So as you can see, for example, in this chart on the right, we start with the total mass. And the total mass influences our wing geometry, which then influences our aerodynamics. Later on, for structure calculations, you get a new structure mass. When you choose a propulsion, you get a different propulsion mass. And when you add those masses up, you get something different that you assumed at the beginning. So you have to restart the process all over again. And so this is called an iterative design loop. And this is what we implemented. And now I'll show you how we implemented it in our case. We start on the left side with our inputs. So our inputs are the high-level geometry of the aircraft, for example, aspect ratio, wing loading, and certain points of wing and empennage geometry. Also with our start maximal takeoff mass, which is also kind of an output. That's why it's a circle there in the diagram, and also our mission segments. Now into the design process, the high-level geometry goes into the geometry module, which is something specific for our case here. We get into that in a bit. And together with the mass, we go into the aerodynamics. The aerodynamics gives a drag polar into performance and propulsion, and also the forces into the structure. And the structure gives us new wing and empennage weights. And on the bottom, our mission segments go into the flight state module, which then gives flight states into the performance and propulsion calculations. And there we receive a new propulsion weight, and we sum all the masses up and see if it converged. If it did not converge, then we start the process all over again. And if it converged, then we have one converged configuration. And also we know how many points we'll achieve with that specific configuration, because this is actually what we want to optimize for. We want the maximum points as possible. So let's go into depth into the applied technology here real quick. We use state-of-the-art software, for example, the PAVA tool from Bauhaus Luftfahrt, which is a 3D aerodynamics calculation tool. Also, a big thing here, we use the CPEX3 from DLR, which is an XML-based parametric data exchange format. And together with that, we use Teagle and CPEX Creator, which is also part of that toolbox. We also use the RCE program from DLR, which can do actually a lot of things, but we use it as our toolchain manager to implement our design loop. So what's special about our design loop process is that the setup is modular. So we can model actually different aircraft configurations. We can model different mission types, and we can also optimize for different criteria. So what this gives us is a huge potential for future applications. For example, different competitions or whatever the future might bring up. Now let's go into the modules of our design loop. So we start here on the left with the inputs. And the first module is the geometry module. So what happens there is that we have the high-level geometry as an input, which is written inside the CPEX file. We can see a part of that here. It's just XML format. And inside the geometry module, the lifting surfaces get created. And the main wing is positioned so that the stability margin is maintained. And as an output, we have the CPEX geometry, which we can see here in the Teagle viewer. And in this format, we can actually continue to perform calculations. Next module is the flight state module. So as input, we have our mission segments. For each segment, we have start and end altitude, acceleration, and so on. We also have our operating conditions, for example, the flight box size that is actually given by the competition. And inside the flight state module, a trajectory gets generated. And as an output, we have our flight states. So we know for each trajectory point, how fast we're flying, what's the acceleration, we know the flight path angle, we also know the time between 2 points and so on. So with that, we can actually do performance calculations. Next module is the aerodynamics module. As an input, we have our CPEX geometry and also airfoil data in 2D polars. And inside the aerodynamics module, we calculate the miscellaneous drag. Also with the PAVA tool, we calculate the 3D aerodynamics. And as output, we have our forces and moments. We also have our twinned 3D polars and our neutral point position. On the right, you can see a screenshot of PAVAT. This is how it looks like inside there. So now let's go to the structure. The structure receives the forces and moments at the critical flight states, also the CPEX geometry and material properties. Inside the weights and structure model, we do two things. So for once, we analyze the bending, and with that, we size the wing spar. And on the other side, we do torsion analysis, and with that, we size our D-box. So as an output, simply we have new wing and empennage weights. And after that, we go into performance and propulsion, which is actually the heart of our design loop. And for that, I happily introduce you, Barlas Türkilmaz.
Thank you. Hi, Tom. So today I would like to talk to you about a little bit how we calculated our performance and propulsion modules. So we start just like we did with every other module. We start with our inputs. We have our 3D drag polar, we have our flight states, and we also have our maximum takeoff mass. With that information, we can calculate how much thrust we need to fly a predetermined mission that we get from the flight state module. And after we know how much thrust we need, we can choose the most efficient propeller that can deliver this thrust. And after we've selected our propeller from a large database, we then go on to select our motor, our cable, and our ESC, which can drive this propeller. And after that selection's successful, we need to size our battery with the amount of serial cells that we need. After we've sized our battery, yeah, here we go. After we've sized our battery, we have our propulsion mass. And after we know our propulsion mass, we need to check if it's converged or not with the previous iteration. If it has not converged, then we have to calculate our thrusts again. And if it has converged, we know which propulsion system we're going to have for a configuration. And we know its properties, its mass, CGs, and we also know how many points we can achieve. So we're actually at the end of our design loop. So we have to check if our maximum takeoff mass is converged. If no, we have to go back, as Heitor already told us. But if it has converged, we know how many points we can get from the competition. And we also know how our airplane is going to look like. So until now, we talked about how we did this theoretically. Now I would like to talk about how we implemented this in software. So what you can see right now is a screenshot from RCE, from our toolchain manager. And all these small boxes that you can see there, those are the modules that we explained beforehand. But one module we did not explain, and that module enables us to conduct parametric studies. And this is that module. This is design of experiments. So how did we optimize? How did we go forward with picking the best configuration? So our goal is, as already mentioned, to maximize energy efficiency. In our case, this is travel distance divided through energy. And to do that, we first of all, we looked at which cruise speed we need to be. After we've determined an optimal cruise speed for all flight states, we did a aspect ratio and wing loading study. So we wanted to determine how our wing looked like first. And then we did a taper ratio study. And after that, we had an optimal wing geometry for a cruise speed. And after we had our cruise speed, we went ahead and optimized the empennage. So how much does the aspect ratio have to be? What does the taper ratio have to be, and so on. And after we did that, we did a propeller diameter constraint study. And that gives us also an optimal propeller. So those are more or less the results that resulted. We have a takeoff mass of almost 13.5 kilos with a wing loading of 14 kilos per square meter. With a aspect ratio of 13, cruise speed of 20 meters per second, a stall speed of 12.3 meters per second, with an energy of, with a total energy demand of 140 watt-hours and with 138 points. And this is how it looks like in CAD. So I would like to thank you for your time, and I would like to give the floor back to Balázs.
And also livery design. So now we heard how we design our aircraft, but how we perform on the airfield and in the workshop. Our next speaker didn't have the opportunity to fly back to Germany due to the currently regulations of the coronavirus. So he is now live from the Turkey. Please welcome on the stage, Batuhan Yumurtacı.
Thank you, Balázs. Hello, everyone. I hope you can all hear me well. So today, I'm going to talk about our prototyping and testing process. All right. So our philosophy is to build fast and fail early. What this means is that starting from day one, we had our prototypes that we have been using as flying test platforms to gain experience, to identify the upcoming problems, and also to find and implement our own solutions. So let me start by talking about our prototypes. The first prototype we have is called Frankenstein. So this is also the model that we have conducted our first flight tests using an autopilot system. One of the main goals with Frankenstein is to check the compatibility of onboard electronics and also to learn how to conduct a flight test as a team. The second prototype we have is called Alpha. Alpha is a fixed-wing aircraft as well. However, we added the vertical takeoff capability by adding the hover motors you can see on the picture to the wings. So Alpha has a quite common quad plane setup, and this is very important because the firmware that we are currently using does actually support that quad plane setup. And the following prototype is called Beta. The goal with Beta is to test the Horyzn setup that we will have in our final aircraft beforehand. So what we are going to do is to attach the cruise motors at the wingtips of Alpha by using the 3D printed motor mounts. And also we will make some changes in the control software such as differential thrust to have the Horyzn setup. The final aircraft we will have is called Gamma. And for Gamma, we are going to use all the optimized parameters from Design Loop and the experience we have gained from our prior prototypes. All right, so how does actually a typical flight test look like and what do we do with our prototypes? So we just don't go to the field and hope that everything works well. That's the reason why we call it a flight test rather than a flight attempt. So before each flight, we set our goals and go through the steps that we are going to follow during the flight test. We have our pre-flight briefing to bring every participant to the same awareness level. During the flight, we have a standard procedure and we go through our test cards. And after the flight, we have our debriefing round where we assess the flight, write down the problems we had, and also the goals we have achieved. And another important aspect about the post-flight is the data analysis. We get our data logs, we analyze them, and also compare them with our prior flight tests. And based on all that information, we go back to the lab and improve our setup. So here you can see some pictures from our flight tests. On the left, you can see the van provided by the Institute of Aircraft Design. Inside that van, we have all the necessary equipment so that we can build our ground control station and have a secure data connection with the aircraft as it's flying. And on the right, you can see an example plot of our data analysis. For instance, this one shows the vibrations during the hover phase of Alpha prototype along each axis of the aircraft. All right, so before handing off, I would like to also mention the flight phases we have and how do we fly with our prototypes. So the first mode we have is hover mode. In the hover mode, we just perform the vertical takeoff like a common multi-copter. Then we switch to transition mode. In that mode, all the motors are active. Thus, the aircraft gains a forward acceleration. Depending on the airspeed and after some threshold, the power is being transferred from the hover propulsion to the cruise propulsion. And after that, we switch to cruise mode. And in that mode, this is actually a typical fixed wing flight. And we just use the cruise motor and the control surfaces. And for the landing, we follow the same procedure backwards. And in that case, instead of accelerating in the transition phase, we decelerate. All right, so now we are going to watch a short video clip from our flight tests. And then to talk about our technical solutions, we will welcome Julian Main. Thank you.
Thank you, Bart, for introducing me. Like he's already mentioned, I'm going to tell you now some technical details of our planned gamma design. So in this slide, you can see what structure we will use. We will use ribs out of balsa wood along the wing profile. Attached to those ribs is a D-box out of carbon fiber. And this gives the whole structure its stability. The advantages of using a structure like this is a high torsional stiffness, a light weight, and a low building effort. So now I'm going to talk about the fuselage design. There you can see that we use some connectors in the edges, and between those connectors are carbon fiber layered boards. But one problem which we have with those connectors, if you 3D print them, there is the danger of getting too heavy. So for example, if you use a radius of 50 millimeters for a connector like this, you get a mass of 1.5 kilogram for all 4 connectors, which is too much for a plane designed for efficiency. So one solution how you can solve this problem is to manufacture those connectors out of carbon fiber. And then you can save around 1 kilogram of total mass. The advantages of a fuselage like this is a high stability and a light weight. So at one point, we ask ourselves the question whether it may be more efficient to taxi with an electric actuated landing gear, which means attaching an electric motor to the rear axle. Because Balázs already mentioned that we have a taxi distance of around 80 meters. So we listed for ourselves the pros and cons of using such a mechanism. The advantages are, for example, that we would get innovation points for the competition. The total energy consumption would be way lower, around 10 times. And noise reduction on ground would also be better. But compared to the disadvantages, which are the added complexity to the system and the weight that is present during the entire mission. And also you can say that such a landing gear is only economic for longer taxi distances. So we concluded that the advantages are only relevant for aircrafts driven by fossil fuels, which is not the case for our design. And I found a quote which sums everything up. Airplanes around the world use over 5 million tons of fuel every year to taxi at airports. So in a nutshell, we can say, yeah, you are way more energy efficient, around 10 times, like I've already mentioned. But so we only have 80 meters of taxi distance in total, which is around 0.5% of the total energy consumed in the whole mission. We do not use any fossil fuels, and the complexity which is added to the whole system is way too overwhelming. So we will not build an electric actuated landing gear. Another question that we told ourselves, because you saw the design earlier with the 4 hover motors. One question was, how can we stop the uncontrollable spinning of the 4 hover motors during cruise flight? So we thought about it to reduce the drag of the spinning inactive propellers and through aligning the propellers with the flight direction. So requirements are a low mass and a small amount of mechanical parts that could potentially fail. In this slide, you can see our solution that we thought about illustrated. Long story short, I will sum everything up for you. There is an infrared sensor in proximity to the rotor, and the sensor can detect whether a white stripe, which is attached to the rotor, passes by the sensor or not. And if the rotor passes by the IR sensor, a signal is generated, which is passed through a microcontroller on which the RPMs and the position of the rotor is calculated. And our flight controller, the Pixhawk, gives some kind of trigger signal to the microcontroller, which then starts its logic, and the relay circuit mentioned down there kind of can switch between normal operation mode and holding operation mode. So with this solution, we try to have as less mechanical parts as possible, a low additional mass, but we also have to say there's extensive testing necessary because we do not want to, we want to prevent states that are not wanted. For example, like holding the rotors during our hovering. So that were some technical details, some of many, I have to say. And thank you for your attention. And now back to Balázs.
So we heard about our aircraft design process from Heitor and Balázs. And Batuhan and Julian have shown our prototyping process, how our prototyping process looks like. But which real-world problems could we solve with our aircraft? From the business team, please welcome Sonja Dluhos.
Hello, as already said, I am part of the business team, and in the business team, we are analyzing a whole variety of different possible use cases for our configuration. One of them would be the organ transport or the shorter ship transport or the defibrillator transport. As we do not have that much time today, I will only be talking about the defibrillator transport. So the defibrillator is a device which is used if somebody has a cardiac arrest, which means that the heart stops beating. So let's take a look at the current process. Right now, if a person has a cardiac arrest and you are a bystander, you should immediately call 911 or in Germany 112. Then you should start doing CPR. The control center will then call the nearest ambulance and the ambulance will come to the scene. That whole process takes about 9 minutes until the first shock can be applied. And the control center also notifies persons called first responders. Those are first aiders which have voluntarily signed up, for example, via the smartphone app Mobile Retter. And those first responders are really important for this use case because you cannot use the defibrillator if there's only one bystander. You need 2 bystanders because you shouldn't stop doing CPR to apply the defibrillator. And it's also important to know that the first responders do not have a defibrillator with them. So that's why we should use UAVs. UAVs, they would bring the defibrillator to the scene so that the shock can be applied. And by using UAVs, we would cut the whole time in half. By cutting the whole time until the first shock can be applied in half, we would add a survival chance of about 15%. Now let's take a look at the total addressable market. If we add up the out-of-hospital cardiac arrests from Europe and from America, we would get 750,000 out-of-hospital cardiac arrests per year. So if we multiply that with the added survival chance, we would be able to save 112,500 lives each year. Now, it's difficult to put a price tag on lives. And we have an institute called the ICR. The ICR is an institute that evaluates new medical innovations and determines when that product would be profitable on the market. The ICR suggests that one quality-adjusted life year would be worth $100,000. A person who has survived the cardiac arrest where the defibrillator was used has about 4.8 years left to live. If we multiply that all together, the total addressable market would be $54 billion. Now back to Balázs.
May you ask a question? What we could do after the NFC competition? Our short-term goal is to collect further experience and know-how in developing fixed-wing UAVs. We will compete in larger competition next year. This will make us ready for our long-term goal, which is to develop a UAV for a specific real-world application. To make this vision become a reality, we will need you. At this point, we would really like to show our appreciation to our sponsors. First, the academic sponsors. We would like to thank to the TUM Department of Aerospace and Geodesy and Dr. Klimke for their support. We would like to we are very grateful to Professor Hornung for supporting our project from the very beginning. Also a special thank to Professor Holzapfel from Flight System Dynamics Institute and Professor Drexler from the Carbon Composites Institute. We are very grateful that the Initiative for Industrial Innovators has supported our project at the very beginning, where we only had the idea. And we are really happy to be a part in the Akka-Modell München e.V. and work with experts in aircraft building to achieve excellent results together. On the other side, we were very happy that all these companies have supported us financially in this difficult time with Corona, and thus enabled us to continue our project. A special thanks to Herr Horst Steinberg, who has already declared his intention to get in contact with the companies and has created a sponsoring platform. Many thanks for the friendly support to Dr. Andreas Stermann, who has also supported us as a mentor. Sadly, we couldn't make our concept presentation personally. But for us, it is very important that you get to know our team. For this reason, we would like to show a video of our everyday life. And now we will say goodbye to our guests by YouTube.